Yep.
So far, so
makes
good?
perfect sense. I'm still tracking with you.
Cool. Well, this is...
Doesn't always happen, John, but you're killing it today.
Oh, good. It's a good day.
You might lose me on this slide, though.
Yeah. Don't get too much in the details, though.
Here comes all the math.
Yeah, sorry.
Hi, everyone. It's Judy. Welcome back to this week's OnTrack podcast. We're glad to have you back again. And this week, our guest is John Coonrod, the Technical Marketing Manager at Rogers Corporation. We met up recently at PCB West in Silicon Valley, and I wanted you to get a taste of the talk he gave there on millimeter wave, RF, and how they interact. So lean in, enjoy. I'll see you on the other side. Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Well, hi, John. Welcome back to the podcast. It was good to see you in person recently, and glad to have you on the podcast again.
Yep. Thank you very much for having me. And yeah, that was PCB West is a really good show, I thought. I enjoyed it. And it's also nice to get out and about anymore, too, you know?
Yeah, that's what I was going to say. It was nice to actually see human beings.
Exactly.
And have a bit of normalcy. We haven't done that in a while. So, for our listeners, before we kick off, I wanted to let you know that as well as John recapping his talk from PCB West, I think I pretty much have twisted his arm to come and speak at Altium Live in the end of January. So registration for Altium Live is now open, and you can go to our website, altium.com/summit, and you can sign up and come learn from John in person. So I wanted to give you that shout out before we get going. Okay, John, let's go into the weeds, and I'll see if I can keep track with you. Sometimes I do, sometimes I don't. So why don't you start by giving us a quick overview of sort of the differences between RF and millimeter wave and high-speed digital, and kick us off with an overview of RF.
Right. Yeah, that's really the right way to do this, is just kind of take it bit by bit, just piece by piece, because these are actually difficult topics to talk about. So I'll try to, do the best I can. And I do have some things to show, but as I show these pictures, I'll also try to be descriptive. But really what happens is for high-speed digital, there is a relationship that's really important between high-speed digital and RF. And if you're at very low digital rates or lower speeds, that relationship isn't that critical. But as you get to higher and higher speeds, like 28 gigabits or something like that, or higher, then this relationship to RF is actually a really big deal. And in RF, I'm just using that as a term for anything that's frequency based, but millimeter wave frequencies, which is greater than 30 gigahertz, the RF behavior is really different. And that's really good to know before you start dealing with high-speed digital or very high-speed digital, because very high-speed digital actually relies on some components of RF. And that's where the interaction is, and that's where things get a little messy. At lower frequency, you don't have to worry about some of this RF behavior. At millimeter wave frequencies, you do. And what they're doing is actually combining different millimeter wave frequencies to make a square wave, basically, or a digital pulse. And as they do that, and these frequencies that make that digital pulse are higher and higher, like millimeter wave range, if the designer is unaware of these millimeter wave tricks, then the pulse is not going to be shaped right. It's going to be distorted, and you're going to have some problems with the digital side of it. So that's kind of a really quick introduction to everything. Does that sound okay so far?
Yeah, that makes sense. I'm tracking with you so far.
Oh, so far so good. Good, thanks. So I guess if you want, maybe I'll step back and just give you a quick, I'll show a picture and just talk quickly about basic RF stuff.
Before I let you go on that, for our audience, I just wanted to say, if you want to see John's images, you can go catch the YouTube version of this. And if not, like John said, we're going to try to be really clear and descriptive as he goes through these.
Okay, I think I'll go ahead and enlarge this just so it's a little bit easier for those who are watching. But to begin with, for RF, and again, this is going to be pretty basic, but I'm showing a picture of a very simple RF system where you have a generator generating RF energy on the left, and on the right's a load that's going to take that energy and do something with it. And what connects them together is a transmission line. And this transmission line is a good example to think about for RF stuff. So the transmission line connects these two things together, but it does have some losses, so it's not perfect, and no matter what kind of transmission line is, what kind it is, it's always going to have some kind of loss, and that's called insertion loss. And being matched in impedance is really important too, and I'm trying to show that in my drawing here, where coming out of the generator, we have out of the generator 50 ohms as the port coming out of there, and I'm showing a transmission line which is not matched at 30 ohms. And that's not a good thing, because when you have an impedance difference like that, you get reflected energy. So you got some energy coming out of the generators trying to reflect right back into the generator, which is not good. And then as you go down the transmission line more, you got another difference in impedance between the 30 ohm transmission line and the load, and more energy gets reflected back. And that reflected energy is called return loss. And the return loss basically corrupts the signal, or it makes the insertion loss numbers not what you think they should be. It makes the insertion loss of the transmission line look higher than it is when the return loss is high. And I bring that up because a lot of high-speed digital, when they're doing these RF evaluations on insertion loss, they report very noisy curves I've seen, and that's not a really good way to do it, even if you smooth out the curve, because there's lost energy because of these reflections. And then you think that your transmission line is more lossy than it really is. So anyway, so that's a quick overview of insertion loss and return loss. Is that okay, you think?
That makes sense. So here's my brain's picture.
Sure.
If you're turning on a faucet, right, and you're putting all this power right through this hose.
Oh yeah.
And then the insertion loss, it's like putting it in a smaller diameter hose, even though that's not exactly a one-to-one description, right? So you're getting less energy, and some of that wants to come back.
Right.
Right,
exactly.
because it's constricted,
Right.
you know.
Yep.
Anyways, am I getting it?
Yeah, exactly. And sometimes
This is like RF primer for Judy. I figure if I can get it, all of our listeners will be like golden.
Yeah, well, I kind of think of it like pipes and water sometimes too. So if you have a really large pipe that has to neck down into a smaller pipe, that's kind of a difference in impedance. And some of that water is not going to go through the smaller pipe, so it gets kind of reflected back to the source. And so it's something like that too.
Okay, that makes sense to me.
All right, cool.
All right.
Well, I think I'm going to move on to another picture real quick. Let's see. So the other picture and the next one after this is really talking more about millimeter wave, and it's really important to understand millimeter wave. Millimeter wave is basically a band of frequencies 30 gigahertz to 300 gigahertz. Microwave is a band of frequencies about 300 megahertz to 30 gigahertz. But the millimeter wave side of this is really important to understand for the very high-speed digital, because that's how the digital pulses are made up, with these millimeter wave waves. Anyway, on a very simple microstrip that I'm showing here, microstrip is just a signal conductor on top, ground plane on the bottom, and I'm showing a TEM, transverse electromagnetic wave. It's basically a plane wave that's made up of electric fields varying that are perpendicular to magnetic fields varying as the wave propagates down the line. And that's the wave that you normally want to use and have information embedded on, or power used, or something like that. And then the next slide is actually showing the same thing except cross-sectional view. And this is one of the big deals with millimeter wave. At millimeter wave, when you go up to these higher and higher frequencies, you can have unwanted resonances. And if the thickness of the substrate between the signal plane and the ground plane happens to be 1/2 wavelength of the operating frequency, then it naturally forms a resonator, resonates a bunch of energy at that frequency, and then it generates its own wave, which corrupts the wave that you do want. So it's an interference thing. Now, if you make that the substrate very thin, then that means that wave would have to be really high frequencies to resonate. So normally, as you go up in frequency, you have to have a thinner laminate to make sure that resonance, unwanted resonance, doesn't happen. And then the same with the bottom picture, except the bottom picture is a resonance from the left side of the conductor to the right side. So it's actually an unwanted wave bouncing back and forth from left to right edge of the width of the conductor. So these are unwanted waves, and they corrupt the wave that you do want. So is that okay, you think?
Yep.
So far, so
makes
good?
Perfect sense. I'm still tracking with you.
Cool. Well, this is...
Doesn't always happen, John, but you're killing it today.
Oh, good. It's a good day.
You might lose me on this slide, though.
Yeah. Don't get too much in the details, though.
Here comes all the math.
Yeah, sorry. Actually, if someone's bored and they want to put this formula in Excel, you'll get exactly what I'm showing here. And what it is a combination of sine waves. So sine waves we can generate very easily, very accurately. So the first sine wave is what we call the fundamental. And then that's just omega t, omega being the frequency. And the next sine wave we'd add to it is 3 times that frequency, 3 times omega. And the next one added to it's 5 times. So they're odd harmonics of that same base or fundamental frequency. And that's actually how they generate these square waves, I guess I'd call it, or digital pulses. And why that's important to know is to the left here, I'm showing an example of what you need to form a 28 gigabits per second signal. The fundamental would be at 14 gigahertz, third harmonic 42, fifth harmonic 70, and the seventh harmonic 98 gigahertz. So the fundamental is not millimeter wave and more than likely not too problematic to deal with. Third harmonic is millimeter wave, and if you don't deal with the millimeter wave issues, then the third harmonic may behave different than the fundamental. So you might have a nice clean sine wave on the fundamental, but the third harmonic could be corrupted by those resonances, and then your wonderful square wave that you want for ones and zeros will not be very square, if that makes sense. And then if you look at 56 gigabits per second, well, that's even more trouble actually for frequency. Now you got the fundamental that is almost at millimeter wave at 28 gigabits or 28 gigahertz. And then the third harmonic's 84, fifth is 140, and seventh is 196. So for this one, the designer really needs to be mindful of these unwanted resonances that can happen at millimeter wave, because then one of these waves will act different than another, and then you won't form a good eye diagram. Eye diagram's made up of these square waves of ones and zeros. And at these high frequencies, it's really mandatory to understand the millimeter wave issues. I brought up resonance, but there's actually several others. So that's a quick overview of how RF interacts pretty directly with very high-speed digital. If this is lower high-speed digital, or not high-speed, but lower speed digital, then all these frequencies go down a lot, and then you don't have a lot of these problems of unwanted resonances and dispersion and all kinds of things that can happen at the higher frequencies.
Yeah, so you really have to pay close attention to these frequencies.
Yep. Yeah, exactly.
Because at some point, does it happen sometimes that you have the fundamental and maybe it doesn't go up into that higher frequency till, say, the fifth or seventh harmonic?
Right, and there is a sensitivity to this too. So what makes up that square wave, it's sensitive to the wave behavior of each of these harmonics, but also sensitive to the magnitude and things like that. So understanding the insertion loss of each one of these signals is also important, besides understanding it's a good clean wave with no resonances and all these other things. So insertion loss is another really big deal too, because if you have one of these waves that are as much worse for insertion loss than it should be as compared to the other, then as they try to account for the difference in amplitude by these numbers that are multiplied here, 1/3, 1/5, 1/7 in the equation, those numbers are trying to account for the amplitude difference of these different signals. But if the insertion loss is a lot higher for the fifth harmonic than it should be, then that's not going to be accounted for properly, and then again you get a distorted square wave or digital pulse. So does that make sense?
That makes sense.
Cool.
In fact, you just made me think of something. I think you and I did a podcast about insertion loss back a ways. So I'm going to, for our listeners, I'll link that in the show notes. So if you want to learn about John talking about insertion loss, that may be useful.
All right. Yeah, so really for the high-speed digital, the very high-speed digital anyway, understanding the RF is really important, and the resonance is already talked about some, but there's other things too. And one of them is related to circuit fabrication, where something like some of the plated finishes, the final plated finishes, they are frequency dependent, where they don't cause as much loss at a certain frequency, and at other frequencies they do because of skin depth. And that's another funny thing that can throw a curveball on it. And a lot of times the high-speed digital is like strip line or differential pair strip line, and in that case you don't have to worry about the final plated finish because the signal is actually buried and it doesn't get the final plated finish. So it kind of depends on the structure too. Anyway, I was also going to talk about eye diagrams a little bit if you'd like.
Yeah, okay. That'd be great.
Well, I'm going to show you a picture of that and I'll see if I can describe that one too. So I was going to talk about eye diagrams because eye diagrams are really wonderful things because they can tell you a tremendous amount about the material, about the structure itself, about the modulation of the system overall, just all kinds of things. So you can understand material behavior here, but it's more than that. It's actually design, it's a lot of things. And the eye diagrams, if you're looking at a perfect eye diagram, it would really look just like a box or a square. And all this is a whole long train of ones and zeros that are laid on top of each other. And you have a differential pair here where one digital train would be going from 0 to a +1, the other one would be a 0 to -1. And when you lay them on top of each other and going through a whole bunch of data like this and lay it on top of each other at the same moment in time, then you get a perfect square. But what happens is when you start having losses, that square starts rounding off, so you don't have that perfect square edge.
See.
You start getting a rounding effect, and then it does start forming a shape that looks like an eye.
Right.
So that's kind of how they came up with that. But what happens is that eye is sensitive to many different things, and insertion loss certainly is one of them. And if you have a material that has worse insertion loss than another, which is really what I'm showing here, the two charts on top our eye diagram of very low loss materials. It is our extreme speed RO1200 materials, extremely low loss, and actually formulated for just this kind of thing, low loss high speed digital. And you can see that the openings for the eye diagram are pretty well defined. And then if you look at another material, same design, same everything, just a different material, and the bottom two eye diagrams, that is, you can see the eye diagram on the left of the shorter circuit. So I'm showing a short circuit on the left, a longer circuit on the right. The one on the left you can see is pretty well defined still, and then when you get to a longer conductor, you have more insertion loss, you have more everything as you get longer, and now that eye diagram is not very well defined and could be an issue. And
isn't your PPE material that you've listed there, is that Teflon?
Oh, thanks. I'm glad you brought that up. I should have mentioned this. So this is actually a non-Rogers PPE materials, because we do have PPE material. But this is a non-Rogers material, and there's a lot of different PPE materials on the market. And this material has been on the market for years, actually.
Oh, it says non-Rogers. I'm sorry, I read your slide wrong. Okay.
Yeah, no problem. But anyway, the reason I bring this up is because this material has been used in high-speed digital for years and years. But as you're getting to higher and higher speeds, it's just not going to be able to cut it until you get something with lower loss. And that's why we're looking at the extreme speed and the upper left and upper right eye diagrams. And really what I'm trying to point out here, and I'm trying to describe this somewhat for those not watching, on the left is a shorter link circuit, on the right's a longer link circuit, and the natural thing is that the eye diagram will close the longer it is. So the longer path this has to go down, less amplitude, less eye opening in a very basic way. So it's a nice way to compare the same circuit with different materials is to look at a difference in length. And that tells you how good the material is at these higher speeds when you need to have conductors sometimes very long, or sometimes not. But it does give you a good comparison of how the material behaves with the speeds and the length and things like that. So is that helpful, you think?
Yeah, I do. I mean, basically it closes down your eye diagram. Yep. That's not what you want.
Exactly.
And I'm just curious about the RO1200 extreme speed laminate you're talking about there, and it sounds like there's a bond ply too.
Oh, right.
I know a little bit about your materials, and I know some of what makes them perform differently is the type of material. Is that relative here? Like, what is Rogers 1200 material? What's the composition of that material?
I get so much in that technology sometimes I don't talk about the materials as much as I should, but it's a really big deal in this case because there's something called glass weave effect, and the high-speed digital industry actually embraced this and understood it long before the RF world did. And really what that means is when the wave encounters a different dielectric constant, it can actually alter how the wave performs. And that's true with RF, and it's also true with high-speed digital. But if you have something like the RL1200 extreme speed laminate, we have it formulated to where the glass weave effect is really non-existent. Even though we do have glass reinforcement, we use a spread glass, and also we have a filler that's really special that also smooths out the effects. So you really will not see a glass weave effect with the RL1200 extreme speed materials.
Sometimes it's better to be lucky than good. So last week we had Bill Hargan on from Z0 talking about glass wave skew.
Right.
So that was last week. So this is a perfect follow-up on
that is perfect
on that, and talking about the laminate's effect. So it does take those things into account.
Right. Yeah. So Bill's really good at that topic, no doubt about it. And so that's really some of the things about the RL1200 material is that it is designed to be very low loss, and it is, but it's also taken into account other things like glass weave effect and some fabrication issues and different things like that. So there is a laminate and also a bond ply, and when they're meshed together, that's going to give you the best case scenario. But we also have a Speedway 300 bond ply, which is actually a PPE-based material, but we've done different things with it with the spread glass and the filler and all these kind of things. So it really does not have an issue either, and gets very clean eye diagrams. But
so what is PPE? What's the construction of PPE?
That's just the base of the laminate, really. So like the RL1200 is a PTFE base with ceramic filler and spread glass. And the PPE material in this case is, like I said, not a Rogers material, but the PPE is, I'm not a chemical guy, and I don't remember exactly what PPE stands for, but that's the base of the formulation.
Yeah, and then, I used to know what that was. It's like
I don't remember.
Polypropyl. It's one of those horrible long names, but
I don't speak that language.
Me neither, clearly.
Anyway, so this material is actually a good material and been used for years and years. But again, as you get into higher speeds, it's just not it's not designed to do that kind of stuff, to be honest. And sooner or later, as they get to these higher speeds, and I've been doing testing at 28, 56, and even 112 gigabits per second, and the RL1200 works really good for that. So anyway.
So I think kind of, if I was summing up what you're saying, is that you need to know these crossover effects and like what frequencies you start running into these problems, insertion loss, and kind of understand these things if you're designing a board.
Right.
And then also use your tools as in the right type of laminate to not exacerbate or, help mitigate some of these problems. Would you say that's a good?
That's all true. Yeah, all the material considerations are pretty much what you said. Copper roughness comes into play too, of course, and we talked about that last time, where copper roughness causes more insertion loss, and it can cause differences in phase and things like that. So using very smooth copper is a good thing, which we use with the extreme speed laminate. So yeah, that's all true. I think that really what prompted me to do this paper at PCB West is that I get a lot of questions from the industry, and some of the people working with very high-speed digital, they did not have an RF background, and they come in and they show me eye diagrams that are pretty distorted, and they don't know why. And once I really start digging into it, then it's really because they haven't considered some of these things, and there's multiple things to think about for millimeter wave. And again, I brought up the resonance thing, but there's others too.
Historically they talk about RF being like black magic, but it's not really if you just know what you're looking at. But I've heard this thing for years, is that the high-speed digital is running right into that RF area, and then things the wheels fall off and people aren't sure because that's not what they've been designing for, but the speeds keep getting faster and faster, and then all of a sudden it's like, oh shoot.
So over the years, the high-speed digital industry has done a lot of really smart things. So once they got up to this limit where the RF is starting to cause problems, they did different things that they could do with processing the signals. So some pretty elaborate digital processing with pre-emphasis and other things to try to help these issues not be as significant. But once you get in high enough frequency, there's only so much you can do. You just really have to deal with the very high frequency components of the digital pulse.
Interesting. Okay, well, John, thanks so much for coming on today.
Sure. And hopefully not confusing too much.
No, if I can get it, I'm sure all of our listeners will.
Oh, good.
So, and I'm sure that was really valuable. So, John, is that you said you did a paper there? Mm-hmm. Is that published and is that available like on the Technology Hub, or where can our listeners maybe get a hold of that?
Right, that was at PCB West just last week ago or 2 weeks ago, I guess. And if you were signed into that, I think you can get the paper. If not, though, we will have that on our Technology Support Hub. I'm not sure if it's there yet or not, but if it's not, it will be soon.
Okay. Well, to our listeners, I'm sure if you've heard John come on the podcast before, we always put in the Technology Support Hub link, because that's where you can go get papers, data sheets. John, are you still doing Coonrod Corner videos?
Yes. I don't know if I like to do them, but I think they're helpful. I just don't like to watch them, to be honest. I don't like to see myself on video, but oh well.
I hate watching the podcast too. Nobody likes to see their image on camera.
Yeah.
I think it's a universal. But
oh, well.
John has a series called Coonrod's Corner, and they're like little mini sessions, like teaching you like a real quick takeaway, and they're really helpful and really good. So those are in there. There's just a lot of great resources there. And so I'll put the link in the show notes below, as well as the Rogers website. And don't forget to sign up for Altium Live. Hopefully John will be there and presenting more of this, or we don't know what the topic is yet, but we'll figure that out. And it'll be something good that I'm sure you'll enjoy. So make sure you go check out the show notes. And John, again, thanks so much. It was great to see you.
My pleasure.
It's good to be out with human beings again.
Exactly.
So,
I feel the same way.
I know. I feel like almost human. Thanks to our listeners for joining us for the OnTrack podcast today. Remember to like, subscribe, give us your comments on YouTube or in your favorite podcast app. We'll see you next time. Until then, remember to stay healthy, stay safe, and always remember to stay on track.